Hello and welcome back to Math with Mrs. Becker. Today in calculus, we are going to hammer through section 2.4, where we will continue to sketch curves, but the goal of this section is just to add in some finishing touches. We will find some x-intercepts, some y-intercepts, and we may even have a function or two that has an asymptote. So let's go ahead and get started. The first example, sketch the graph of y equals 1/2 x squared minus 4x plus 7 using the first derivative test and the second derivative test. You guys, that's the exact same thing that we did in section 2.3. Okay, so as we're doing 2.4, we will start off with the exact steps that you have been practicing. The only difference is we'll be sprinkling in a couple extra points at the end. So let's go ahead and I'm going to rewrite my function in function notation. So f of x is 1/2 x squared minus 4x plus 7. That's the original. We need the first derivative. 2 times 1/2 is 1. Reduce the amount of x's by 1, so I just have 1x. Minus the derivative of 4x is 4. The derivative of 7 is 0. So my first derivative is x minus 4. Now you find the second derivative. The derivative of x is 1. The derivative of negative 4 is 0. So that is step 1. Now remember, the first derivative helps you to identify extreme points. Those are your possible maximums and minimums. So if I want to find extreme points, you take the first derivative and you set it equal to 0. My first derivative is x minus 4. If I set it equal to 0, I would have to add 4. So I have a possible maximum or minimum where x equals 4 because at that location, the slope is 0. Now to see if it's a maximum or a minimum, you fill it into the second derivative. If I fill a 4 into the second derivative, I get a 1. 1 is a positive value, so that means that it's concave up. So remember, it curves up at that point. That confirms that this value is a minimum, because if it's concave up, that point is at the bottom of the curve. So at this point, I know that we have a minimum where x is 4. To find the y value, you have to go back to the original function. So if I do that, I have 1/2 times the x is a 4, so it's 4 squared minus 4 times 4 plus 7. We get negative 1. So that's the first point that I can plot. Let's go ahead. Our whole goal here is to be able to sketch. So I want to get started. If I go to the right 1, 2, 3, 4, and down 1, there's a minimum point. At that location, I know I have a slope that is 0, and I know that it's curving that way. So that's what we know so far. Now what we want to do is see if we have an inflection point, a point somewhere in the graph where it's going to change from concave up to concave down, meaning it's going to change on whether the graph is opening upwards or opening downwards. To do that, you take the second derivative and set it equal to 0. Well, if I take the second derivative, it's 1. 1 equals 0. Well, there's nothing to solve for because there's not a variable. 1 does not equal 0, so we have no inflection points. I know that because the second derivative, if I set it equal to 0, I ended up with a false statement. It said 1 equals 0. We're done. Okay, so all I know right now is that. From 2.3, we're done. Okay, that's why they're saying, well, let's do some finishing touches. How about we find a y-intercept? Now, a y-intercept, that is where your graph crosses the y-axis. Now, if you're thinking about this, if you cross the y-axis, that means you do not go to the right or the left. So when you are trying to find your y-intercept, that's the location where x is a 0. To find out your y, you always go back to the original. If I put a 0 in for x into the original, I end up with a 7. So here's another point I can graph. 0, 7. 1, 2, 3, 4, 5, 6, 7. Hey, we got another point. Yes. Okay. Now x-intercepts. X-intercepts are your zeros. More often than not, when you are going to go ahead and find your x-intercepts, it's when it's in quadratic form, meaning you'll be able to find your zeros using the quadratic formula or factoring. So if I go ahead and I want to find the x-intercepts, and I have 1/2 x squared minus 4x plus 7. Let's jump to the quadratic formula. A is always the number in front of your squared term, so in this case it's 1/2. B is always the number in front of x, it's -4. C is the number at the end, it's a 7. Underneath the radical is b squared minus 4ac. B is -4. Minus 4 times a is 1/2. C is 7. If I calculate this, this tells me what goes underneath the radical. -4 squared minus 4 times 1/2 times 7. Underneath the radical, I have 2. This tells me that I do have 2 solutions. I have 2 x-intercepts. Remember, if your discriminant, that's what this is called, if it's a negative value, then you have no real zeros. If it's a 0, you have 1 real 0. If it's a positive number, then you have 2 real solutions. So we are going to be able to find 2 x-intercepts. Let's keep going with the quadratic. X equals -b. B is a -4, so it's +4, plus or minus the square root of 2, all over 2a. A is 1/2. 2 times 1/2 is 1. Well, if I take anything divided by 1, it's not going to change it. So my x-intercepts are located at 4 plus or minus the square root of 2. Yes, I'm going to end up with decimals. Totally fine. If I go 4 plus the square root of 2, if I round it to the 10th, I will have an x-intercept at 5.4. If I go 4 minus the square root of 2, I end up with 2.58, so if I round it to the 10th, it's 2.6. So let's go ahead and plot those 2 points on the graph. If I go to the right 1, 2, and a little bit more than half, my graph has to cut through that point. If I go to the right 1, 2, 3, 4, 5, almost to the half, my graph has to cut through that point. Now look how much this really did add a lot more dimension for us. I feel much more comfortable going ahead and connecting the points now, just having those intercepts. So again, you start off with the same skills as 2.3, first derivative, second derivative, looking for maximums and minimums, first derivative, set it equal to 0, solve. To see if they're maximums or minimums, you fill them into the second derivative to see if it's concave up or concave down. Inflection points, second derivative, set it equal to 0. This graph happened to not have any. Y-intercepts, x equals 0. X-intercepts, you will use skills like factoring in the quadratic formula. Here is our sketch. Yes. Okay, let's go to the next one. This says there may be graphs that do not have critical points. So that means as we're going through this process, you might have things that have no maximums, no minimums. The last example, we had no inflection points. Okay, so don't be alarmed if you end up with some of those things. That is going to happen. And that's what 2.4 is really doing. They're having us practice the skills we've been working on, but they're throwing us a few curveballs. Okay. First thing I want to do, here is my function. It's in function notation, so I'm just going to go ahead, jump to the first derivative. If I take 3 times 1 over 6, that would be the same thing as 3 over 6, which would reduce to 1/2. Reduce the amount of x's that I have by 1, so I have 1/2 x squared, minus 3 times 3 halves. If I multiply the denominator by itself, so if I take 2 and the denominator is a 2, remember they cancel, that will leave you with 3. Reduce the amount of x's by 1, so you would have 3x. The derivative of 5x is 5. So my first derivative ends up being 1/2 x squared minus 3x plus 5. Second derivative, 2 times 1/2 is x, minus, okay, sorry, 2 times 1/2 is 1. I reduced the amount of x's by 1, so I just have an x. Minus 3x, it's just going to be minus a 3. The derivative of 5 is a 0. So here's the first process, the first steps. Now, if I want to find any maximums or minimums, you take the first derivative and you set it equal to 0. So I'd have 1/2 x squared minus 3x plus 5 if I set it equal to 0. I am going to go ahead and try to use the quadratic here. This is a quadratic equation because I have 3 terms. The exponent, the highest exponent is a 2. I know I need to find 2 solutions because I have a degree of 2. A would be 1/2. B would be -3. C would be 5. if I go b squared minus 4 times a times c. Let's calculate the discriminant. Negative 3 squared minus 4 times 1/2 times 5. I get negative 1. So you guys, whatever you get here, that's what goes underneath the radical. So within the quadratic, I would have x equals negative b, so it'd be 3 plus or minus the square root of negative 1 all over 1. A negative underneath the radical means it's imaginary. So this tells me I have no maximum or minimum points. So this graph that we are going to be creating pretty shortly here has no locations where it switches from increasing to decreasing or decreasing to increasing. Okay, let's check and see if maybe we have an inflection point. You take the second derivative and set it equal to 0. The second derivative is x minus 3. If I set it equal to 0, x would equal 3. So I can do that variation table. Remember the variation table from 2.3? 3 is the location where the concavity is 0. So if I pick a value lower, like 2, and I pick a value higher, I want to know if they're concave up or concave down, because I want to know if that concavity switches here. In order to check concavity, you have to put these values into the second derivative, because we're checking for concave up or concave down. If I put in a 2, 2 minus 3 is negative 1, so it's concave down at that point. 3 is where it's not concave up or concave down. 4, if I put in a 4, 4 minus 3 is positive 1, so at that point it's concave up. So yes, at 3, that's where the concavity changes. Again, to see if it's an inflection point. Second derivative, set it equal to 0. To use a variation table to check for concavity, you choose a value to the left and the right, and you have to put it into the second derivative to check and see if they're concave up or concave down. Because I have a negative value on the left and a positive value on the right, I know that yes, this is an inflection point. Well, I want to graph that. Right now, I only know the x value. So the x is a 3. In order to find the y, I have to go back to the original function. So 1/6 times 3 to the power of 3 minus 3/2 times 3 squared plus 5 times 3 plus 1. I get a 7. So in my graph, there is a point at 1, 2, 3 to the right and up 1, 2, 3, 4, 5, 6, 7. This point right here is an inflection point. Okay, if I look here, it's going to be concave up. So that means the curve is going to be up above the tangent line here, but here it's concave down. So this is what's going on at that point. It has a little swoosh. Think back of college algebra when we talked about multiplicities. Remember if you had an odd multiplicity, sorry about that, if you had an odd multiplicity that was greater than 1, as across the x-axis it bends, it's kind of the same shape as what's going on here. At this point, it's concave up here, concave down. So we know that. Yes, okay, we're rock stars. Now, if I look at y-intercept, let's see where this bad boy crosses the y-axis. Y-intercept is where the x value is 0. To find the height, the y value, you have to go back to the original. So if I put in a 0 for x, this cancels, this cancels, this cancels, the y value is 1. So at 0, 1, I have a point. Now here's the deal with your x-intercepts. You only have to find them if you have something that you can easily factor or if you can use the quadratic formula. So this one, we get to omit any x-intercepts. You do not have to find them because this is not anything I can easily factor. I cannot do the quadratic formula because this would be a difficult task. You are allowed to omit that step. Y-intercept, though, you'll never have to omit that. All you do is put in a 0 for your x's. So this is all you'd have to have. We did our first derivative, our second derivative. We did not have any maximums or minimums. We do have an inflection point. We found an intercept. That was enough where we could sketch and get a visual of what's going on. Last one. Graphs with asymptotes are going to start showing up in this section and later on in the chapter. So we want to graph something with an asymptote. So let's go ahead. F of x is x plus, remember 1 over x is the same thing as x to the negative first power. Right away though, back to our college algebra knowledge. This is going to give us an asymptote because it's breaking the domain. Remember, with the domain you have two rules. One rule is you can never divide by 0. The other rule is you can never have a negative underneath a radical. Well, here I have a variable on the bottom of a fraction. So x can never equal 0. You guys, that's an asymptote. X can never be a 0. So what happens is you are not allowed to ever have a value that's on the y-axis because at that location, x is 0, and that would make the bottom of the original a 0. Okay, so that is an asymptote. Now let's go ahead and find some derivatives. Your first derivative, the derivative of x is 1. Here, I bring the negative 1 out front, keep the x, reduce the exponent. Your second derivative, the derivative of 1 is 0. Negative 2 times a negative 1 is 2. Keep the x, reduce the exponent. So I still found first derivative and second derivative. The first derivative without the negative exponent would look like this. 1 minus 1 over x squared. Your second derivative without the negative exponent would look like this. 2 over x cubed. So far, though, I know I have an asymptote because I cannot have x cannot have a value that's 0. Let's go ahead and see if I have any maximums or minimum points. So I take the first derivative and I set it equal to 0. If I go 1 minus 1 over x squared and I set it equal to 0. Well, if I go ahead and minus 1, negative 1 over x squared would equal a negative 1. If I divide both sides or multiply both sides by a negative, the negatives would cancel, so I have 1 over x squared equals 1. I don't want my variable on the bottom of a fraction, so I can go ahead and multiply both sides by the denominator. So 1 equals 1 times x squared is x squared. To cancel a power of 2, you take the square root. Because this has a power of 2, that means I'm actually finding two solutions. For that reason, the other side has to include both the positive and negative. The square root of 1 is 1. So this means that I have possible maximums or minimums at x is positive or negative 1. However, if I go ahead and I look back at the original problem, the domain, they said that we're only focused on what's going on if x is greater than 0. Sorry, I had to throw my colored pencils because the light went off. All right, we're going to keep going. So if you heard that, that's what was going on. If the light was doing funky things, obviously I'm not moving enough doing these notes. All right, keep going. So I went ahead, I set the first derivative equal to 0, and I solved. I found that I have maximums or minimums, or possible maximums or minimums, where x is a positive or negative 1. Here, they only want us to worry about the right side of the graph. We do not have to worry about this because they're telling us that this function that we're looking at is defined for x is greater than 0. So we're only here. So the only one I have to test is x equals 1. That is a possible maximum or minimum. To see if it's a maximum or a minimum, you fill it into the second derivative. So second derivative, if I put in a 1, it's 2 over 1 cubed. Well, 1 times 1 times 1 is 1. 2 over 1 is 2. So at x equals 1, if I go to the right one, that is where I have a slope that's 0. This is positive, so it's concave up, which confirms that we do have a minimum. So I have a minimum where x is a 1. To find out what y is, I have to put 1 into the original function. If I put a 1 in, it's 1 plus 1 over 1 is 1. 1 plus 1 is 2. So if I go to the right one and up 2, this is where the slope is 0 and it's a minimum, so I know it's like that. Yes, okay, got that. Now, the next thing is we want to know if there's any places where it is concave up or concave down, like the switching. Okay, we're looking for an inflection point. To find an inflection point, you take the second derivative and you set it equal to 0. Our second derivative is 2 over x cubed equals 0. Well, to cancel a denominator, I would multiply both sides by x to the power of 3. This cancels, 2 equals 0. So this has no inflection points, okay? We don't have that. Alrighty, so I don't have any inflection points. I do have a minimum point. Y-intercepts. All right, let's find some y-intercepts. It's kind of crazy trying to keep this organized. Y-intercepts. That's where x is a 0. So if I put in a 0 there, oh, I can't put in a 0 there because 1 over 0, that doesn't fit in the domain. So you guys, I don't have any x-intercepts. If I look at this, it's going to curve upwards, so I don't have any x-intercepts, I don't have any y-intercepts, I don't have any inflection points. So at this point, the only thing I can really do here is fill in some points to try to figure out what the heck is going on. So we go back to the good old XY table. If I want to know what's going on or how high or how low this graph is going, I'm going to go ahead and put in a few points. So this is 1. I'm going to put in like a 2 and a 3. So if I go x equals 2 and 3, let's go ahead and go to the original and see what's happening here. If I have 2 plus 1 over 2, well, that's going to be 2.5. Got that. So if I go to the right 2, I go up 1, 2 and a half. So I can see, yeah, that makes sense. Okay, if I go 3 plus 1/3, well, that's 3 and a third. So I go to the right 3. So I can see what's happening is it's going to go up like that. When you're dealing with vertical asymptotes, that's where your graph has to shoot up to positive infinity or shoot down to negative infinity. Well, in order for this to be a minimum, that means this must curve up, so that would go to positive infinity. Now, what we actually have here, and they did not go through how to find this. This was a skill we talked about in college algebra. Notice we have what's called a slant asymptote. This slant asymptote occurs at y equals x. As you can see, it doesn't parabola up like a quadratic would. It kind of veers off. That's because there's another asymptote there. But what you would have to be able to do is find the first derivative, find the second derivative. We had a minimum. We were only looking at values to the right because we said that x had to be greater than 0. There were no inflection points. There were no y-intercepts. There were no x-intercepts. So the only thing that we really had, you guys, was this. So at that point, you do have to realize that if you want to have a visual representation on a graph, you need to find ordered pairs. Well, the way you find ordered pairs is you go back to like 7th and 8th grade skills and you make an XY table. You fill in values of x where you want to know what is the y value. You always fill it into the original, you get your image. Okay, there are 12 questions in the book that I think are pretty darn good practice. I also have made and included in your Google Classroom a little cheat sheet, okay? So this is a combination of 2.3 and 2.4 because I know it's a lot. And kind of the most difficult part is trying to make sure that you don't forget anything. Okay, so when you're going through and doing the assignments, you will get to use this on the exam as well. This just kind of is like a step-by-step guide. The first thing that you want to do if you are sketching a curve, you find the first and the second derivative, always. Okay, number 2, if you are trying to find relative extreme points, those are maximums and minimums, you take the first derivative and you set it equal to 0. Okay, and then it just goes ahead and it tells you that you find those values. If you fill them into a second derivative and it's positive, then it's concave up, so you have a minimum. If you fill that value into the second derivative and it's negative, then it's concave down, giving you a maximum. If you set it into the second derivative and it equals 0, chances are you don't have a maximum or a minimum. It wasn't positive, it wasn't negative, it wasn't concavity, so you'd have to go ahead and look and see how it changes from increasing to decreasing to help you complete the graph. Then you find inflection points. To find inflection points, its second derivative, set it equal to 0, solve for x. okay? Then you go ahead and compute, that's the point. Test concavity going to the right and the left, that's that variation chart that we looked at on one of the examples that we just completed. Then consider other properties. Find your y-intercept, that's where x is a 0. Do a partial sketch. Are there x-intercepts? And again, if it's something that you can do the quadratic formula or factor, find your x-intercepts. If it's something crazy like powers of 4 and powers of 3, don't worry about it. You get to omit it. So if you can find it using the quadratic or factoring, do it. Otherwise, don't worry about it, okay? Observe where the function is defined. So that's like the last example. What they told us in the last example, it said that this is defined for x is greater than 0. So that's why we only went ahead and graphed on the right side. So you have to be careful. Lots of times when they give you problems, they're going to tell you where it's defined. You want to make sure that you only graph those x values. Then look for any possible asymptotes. That's where you would look and say, all right, is there a place where if I put a number in for x, that the bottom would end up being a 0? If the bottom of a fraction ends up being a 0, like we had in our last example, you get what's called a vertical asymptote. So this is just like a step-by-step guide that I would just print off and keep next to you as you're going through these problems. And again, these 12 questions in the book will really help you to further understand what's going on in 2.4. I hope you guys had a great day, and I'll talk to you soon.